Okay, thank you, Min, for inviting me and setting up this talk, and thank you, everyone. I hope you can hear me online as well. And here I'm here to present. This is going to be a general presentation about the research we're doing at IIT, and that's actually also how we structure the research of the institute. As you probably know, IIT and Rick and AIP, they made an agreement for exchange. Some of your people have come to visit us in Genova, Italy, and some of us as well has come here to give us workshops all together. We did one last year when we came from ICRA conference in Yokohama. We stopped over for a couple of days in Tokyo, and I hope you remember. So, as Min was mentioning, I'm going to stay here 1 week. This is a general overview of the research we do at IIT, plus some research I'm doing specifically in my group at the Institute. So this is a good startup. So if you want to meet me, then you can drop me an email. We can set up a visit here in Tokyo. So I do a brief explanation of what IIT is. At the moment, IIT is the Italian Institute of Technology, is a private foundation that is funded by the Italian state for around 100 million euro per year. At the moment, we are around 12,000 people. It's very difficult to track the exact numbers of people we have at the moment, but let's say this is the size we have. We are quite a young institute in the sense we started like around 20 years ago, but also we have an average age which is approximately about 36 years old. Of course, we're growing as well. I'm growing as well, so increasing this mean somewhat. And we have scientific staff, which is the PIs, researcher, postdocs, technical staff, and PhDs. That is about 80% of the total. So it's a lean organization with only 20% of administration. And we have as well a good ratio between let's say, Italians working in IIT in Italy is 48%, but we have a good number of foreign people, almost 30% outside, and we have a part of Italians, 20%, but it came back to work in Italy from abroad, which is a very good thing to attract back our talents in Italy. So we have staff as well from more than 60 countries. So we are highly interdisciplinary, or something that we really like. We have a good ratio balance between male and female. So almost a gender equality. And as I said, the budget of IT is around 100 million, but we have as well part of it coming from external project. So a good part of this money is coming from our endeavors in collecting external grants and collaboration with the companies. So the institute have a strong view and strong commitment in working with the industrial, let's say, texture of Italy and also internationally with other companies in order to attract other funds and also provide the technology to these companies. And as you see from this image, IIT is well spread not only in Genova, which is our main part where we are based on here in Genova, but we are well spread with the centers that are in conjunction with the university in the north, center, and south of Italy, all around the country, plus 2 outstationed the United States in Harvard and MIT. So this is the part that I'm gonna talk mostly today. IIT is also providing developing a strategic plan like the industrial plants and companies are doing of 5 years, where we state our research and our objectives that then are going to be evaluated by our scientific and internal committees of the institute. We are divided in general in 4 main domains in research. One relevant one related to robotics, nanomaterials, life tech, that means life science technology for life science, and computational science, where I'm working and other machine learning colleagues are working on as well. So this was what we were divided in the past, and the moment we decided a few years ago to not only have this structure in divided by domains, but also to have a different structure based on some flagship programs we developed in IIT. In general, these flagship programs are more horizontal in respect to the domains. So it means that we cluster together other researchers from the institute to address some tasks that have a practical impact in our society and in the world. So this was a need in order not to reason in silos in our institute, but to have an interdisciplinary, more interdisciplinary flavor in our activity, also with a very precise target. So what we call our general open research is called a Blue Sky Research Program, and is a research that we do actually related to topics that the PI decide, and they are based on the scientific excellence. Then we created the 5 flagship programs, as I said to you, that are related to different problems. One is technology for sustainability, so to provide technology systems to help our sustainability and ecology and other in power consumption and other themes that are very important for our society. Brain and machine, that is related to the fact of studying how the functioning of the brain and how this can be translated in machines, such as in a robotic system. RNA technology, which is by itself pretty much self-explanatory, and teaching science to computers to create AI machine learning methods that can support scientific discovery inside the institutes and outside for it, and also technology for healthy living. So technology to support in general aging society, which is a very important topic for Italy, also Japan, of course, because we are one of the oldest one of the fast aging countries in the world. So this was a quite complex procedure. We started bottom up well before 2024, where PIs were proposing these flagships. Then they've been consolidated into this main branch and managed by some coordinators. So these type of flagship are very important for the future, and they will be first evaluated in 2029. If you have any question, of course, you can do it and interrupt me during my my talk. Okay, if you want to be, it's good to be interactive anyway. So if you have any doubts, please let me know. So I would like to go through this flagship, but given the time I have, I'm gonna focus mainly on some aspects of Blue Sky, on brain machine, teaching science to computer, and technology for healthy living. But for the rest, I'm always available here to talk with you. So for Blue Sky Research, I just show you some 2 topics, which are very important for the Institute at the moment. and is the molecular dynamics. And these slides show you how molecular dynamics is quite extensive in terms of times. It can relate to femtoseconds when we model like a bond vibration at a very small molecular atomic level, where we can have very accurate models, quantum models that can model these interactions. And then to picosecond, we go to proton transfer, which is one part related to the acid-basic interaction that can scale up with the time as well with the complexity. And with the tool used in this way, we still computationally try to express and model this type of interactions in the matter. While we go into diffusion in liquids that goes through microseconds and nanoseconds, the interactions, also kinetic interaction, becomes much more complex. And here, not computational tools becomes less efficient to deal with them. And so in this case, we need also machine learning to try to reduce the time of computation. When we go for chemical reactions in terms of milliseconds and seconds. These interactions are much more complex because we have a very strong variation when the atoms bind them together. This type of variation are indeed very complex, and they happens in a very precise instant in time through a longer time extent. And then we go toward even more complex molecules variation that has to be modeling like protein folding that can take seconds and hours to phase transition of large arrangement of molecules. Here we, of course, have to tackle all of these molecular dynamics timescale problems with the different tools that are heavily based in computation, needs the support of machine learning in order to model this complex variation in a reasonable amount of time. One of the aspects of blue sky research we are doing now and that are trying to solve real problems is related to plastic, which is a problem that affects our environment in a very strong way. We are developing an enzyme that can process this plastic. This enzyme, of course, they can do this at the moment, but with a very slow rate in time. So we are trying to find some variation of this enzyme. And here we use molecular dynamics in order to understand which changes in the enzyme can provide a faster process and decomposition of the plastic in our environment. So in this case, again, one of the things that can be used is in the lab experimentation. So trying to do mutation of this enzyme experimentally, but this takes time. And one aspect we are working on is to try to use AI and HPC in order to screen out the variation that can provide a much better functioning on the enzyme in decomposing the plastic. I will go to some computational aspects which are very interesting. One of the first flagship I'm going to talk about, it's called brain machines. This is trying to connect together neuroscience and robotics. So to study computational models of the brain and trying to find a way to apply these computational models into machines like the robotics that IIT is developing that has developed through these many years. So here the idea is to collect together many PIs from IIT, from life tech, that includes neuroscience, from robotics and computational science, and also other infrastructure that are related to three facilities, under three coordinators that are multidisciplinary between different fields on robotics, social robotics, and neuroscience. So this is a large amount of number. You see also myself here, so you can understand that it's not easy to coordinate with flagship, and their implementation is really strategical about to give the right success given the KPI we have put in together. So the ambition of this flagship is to understand, of course, intelligence in both biological and artificial systems. And somehow we have ways to visually inspect neuronal circuits and their application in order to decode the codes of the brain doing some task, for instance, in the mouse about navigation, and somehow try to distill this computational model and trying to apply them into computational system like robots in order to improve to prove and improve these models in building the intelligent machine. So the goals is really to have this multi-scale, multimodal description of brain activity and behavior, and build a computational model from it, and then try to translate this model into the behavior, for instance, of a robotic system, as you see in this video where the robot is doing some actions from some visual activation. And indeed is to boost up the autonomy of this intelligence system. So these are divided in four, let's say, main topic that are computational, cognitive, embodied AI, and clinical. From the computational aspects, the main problem is really to decode this brain activation at a different scale in the brain. From the cognitive aspect is to study these models and the application in embodied AI setting. And also one aspect is also very interesting to find some ways to study also some clinical aspects, especially for neurobehavior of people. So of course, one result that is quite easy to see is the fact that at the moment we can train robots to react to people input. This is one of the final aim. These are some initial results where robots can be activated by some visual stimuli, means from the camera they see, and also they can at the moment understand also some language, of course, here in this case using a large language model, but the idea is to go towards more neural-inspired approaches in this type of reactions of our robotic platform. So another aspect that is very important, and I know that some people here working on, is about the flagship on the technology for healthy living, where here we have two coordinators again from technology and then from medical science. And we are addressing the aging population problem. As I told you before, Italy and Japan are a very good example of this aspect. This is a projection that was made in 2019 about the aging report about of the European Commission about Europe. You see that in these plots, these bars about male and female population, where in light blue for the male, you see the distribution of ages of population given the different ages, and this distribution 27, you see that dramatically this distribution starts to become uniform. You see that the rate of people over 90 years is increasing pretty much, but actually the people from 65 to 90 is a big portion of the population in respect of the working population. So this is an issue for our health system because multimorbidity affects more than 50% of people at age 65 plus, and there are 800 million people at 65 plus already in 2025, and they're going to be 1.6 billion in 2050, and 500,000 of centenarians already in 2050. So this is a good sign because our life expectancy is increasing. This is good, but this is indeed a major issue. So the technology for healthy living flagship is developing robotics and AI for assisting people, because the other issue we are going to have is that we're going to missing hands in supporting people. So our health staff is not enough. So we need to deploy new technology for supporting what is happening, and to deploy smart drugs and sensor to monitor as well people from outside and within, and also novel holistic approaches that integrates both the two topics I told you before. This flagship had a different approach in respect to the others, because we started in identify 4 use cases that were pretty relevant, and also in the course of the research that IIT was performing during this year. So we decided to study 4 use cases. One is stroke and neurodegeneration. So improving clinical effectiveness, exporting clinical practice to telerehabilitation approaches, brain cancer, to transform highly aggressive tumors into manageable chronic diseases, and also use case 3, which is musculoskeletal frailty, so monitoring and intervention in osteoarthritis and other musculoskeletal disorder that affect people, even not aging person, but also workers in the environment. And then the last use case is related to sensory impairment, that is related to creating multimodal assessment and treatment framework for, in particular, for vision impairments, where we have already some very good example of research in IIT. This has been, again, a quite interesting effort in enrolling different researchers that works both in robotics, social robotics, neuroscience, and drug discoveries and therapeutics, smart therapeutics, in order to provide to tackle these 4 use cases. So this is well spread throughout the IIT staff and network at the institute. And not only we are trying to bond some collaboration also internationally by support ourselves with the university that have a strong linkage with the clinics and hospitals and laboratories. It would be great to have here our Japanese counterpart somehow in this map. And so this is also one of the reasons I'm coming here to discuss about these problems and potential collaboration. So for this stroke rehab, you will see a lot of this technology through my presentation. We really need the system to monitor people, in the sense that we need to assess 24 hours, but also on the long term, the type of activities person are doing in their daily life, especially when they've been affected by disease, in order to understand if a critical situation arises. Not only we have to monitor them, but we have to design our system to be to respect their privacy. So privacy by design, the strong element we have to deploy. Of course, you know that Europe, we have documentation that are acting upon AI systems, so we have to not only research them, but to make sure that these systems are also deployable in reality. We have also now we also having active systems or robotic platform that not only can be activated if a person is in need, so they can perform some task. And the moment we are working to deploy both a spatial awareness of the robot about the area where they navigate, but also to understand the language input from them and to actuate different actions inside the environment given precise issues and the state of the person. So the sensors are not only deploying on the environment, but can be also active as being deployed on the robot. One of the other objective, as I told you before, was about the musculoskeletal frailty. Here we have again a part related to the monitoring, but in this case we are very interested of the posture of the person, especially when they work in a working environment, because these problems affects a lot workers that needs to carry weights or do repetitive actions during the day. And we are developing also vibro-tactile feedback for functional rehabilitation. This is something that is coming to support people without use the exoskeleton. Actually, is something that can be wear at your wrist that can give you some vibro-tactile sensing if you are doing or having a posture that possibly leads to a musculoskeletal problem. And also to create, sorry about that, to create a robotic system that can support the workers during their activity and in an active way, so reducing the stress over the worker's back, and especially on the column, that can be the main reasons of disease in the worker's life. One other objective we have, especially with amputees, to create a new prosthesis. Here I show you two examples. One is Unico, that is an intelligent prosthesis that can indeed be calibrated to personalize to each user. And the other one is Softfoot. This is Softfoot is a passive prosthesis, so it's not actuated, but has a strong skill of adaptation, so it can really naturally model and a real foot of a person differently from different prostheses where they're quite flat in the foot part, especially when going on different type of terrains. The idea as well is, for instance, for the intelligent prosthesis is to have as well monitoring system that can support and fine-tune the prosthesis given the working skill of the person and the gait they have in particular during their own activities. And it's very interesting that this prosthesis I'm sure you have been also winning in competition, and IIT achieved the second prizes Cybathlon that was last year, and also and as I told you, the monitoring part is very important, and we are actually collaborating with hospitals at the moment and the institution in Italy. One is Galera Hospital, but he has a section of the hospital is very on the state of the art for geriatric cures, and also Gaslini Hospital more about infant and pediatric hospital, and also we are collaborating with FISM, that is Institute for Multiple Sclerosis, and with all of them we are deploying monitoring solution that are able to estimate parameters that are very important for them about mobility, activity level, strength, and other aspects that relates to aging and the well-being of people. And the interesting part and more complicated part is to try to understand which parameters have to be computed, extracted, and then summarized for the staff to understand if a patient is improving or responding to the therapies. This is just an example of our dashboard at the moment. On the right, you see the information we extract in a prototype room for observation. Here we have in this room a part camera. We have sensorized bed, as you see here, that can detect where a person is sitting, laying down, so giving an information of their daily activity, as well as sensorized chairs that do the very same tactile response. And also we have here a floor which is sensorized that can give you trajectory velocity of the person through time during the day. And here in the panel, we update, here you see a mobility index that providing an information of the different actions that happen during the day, their proportion, and the computation of a mobility index in real time. So this information is then used for the clinician, or they can be integrated into medical index or medical summary for the patient. And at the moment, this is only one of the indexes we are studying at the moment, but the experimentation is going on with other entities that needs other parameters to be extracted. So I'm going now to the last flagship I want to present you today is Teaching Science to Computers. That the research interest of this flagship is to create machine learning AI models in order to support the research, the scientific discoveries at IIT. And one aspect I told you, which is very important for us at the moment, is molecular dynamics simulation, artificial intelligence in the broad sense, data science, that are pillars for our research mission. But anyway, you see that AI is well spread in through all the research of IIT and is very strategical for different aspects. But this is not only IIT, but is a trend that is worldwide. So the program is combining fundamental physics laws, domain knowledge, and foundation of machine learning in order to achieve this task. We have an additional investment in these years. We had a 3 petaflop high performance computing increase and 10 petabytes of storage because some of the data we have really needs a large amount of data, and the challenge is really to create physics-informed AI algorithms and simulation-based methods to maximize the impact of computational experimental work in science and engineering. And this has been divided in three different elements, in 3 different objectives. I'm gonna go through a bit more on the physics-informed or machine learning algorithms we are developing. In my case, I'm very interested in finding architecture that can deal with multimodal data and to deploy machine learning algorithms that solve tasks that using this type of information. And in general, this information can come, in my case, or in many problems robotics people are working on, with the using two type of data, for instance, RGB and depth information, but also the information that comes directly from the robot, like the currents that we provide to the engine, or as we have from the feedback of the engine, and those other parameters that are related to all the sensor installed from the robot. These are in general 1D or few D signals in compared to RGB and depth, and the idea is try to fuse this information, for instance, to solve a task to provide the joint position for the robot in the next few seconds. So for the robot to react to some input information from the cameras and from the sensor itself. So to make the robot reacting to the stimuli that you obtain from the environment in order to achieve a level of autonomy that I will further talk later. So indeed, we need to have both models to try to find cross-modal attention. So also when input data arrives, in order to understand which token or element of the data is important for performing the task, but not only at a specific time instance, but also to have a temporal attention in order to understand which element of the sequence of data we obtain is relevant for solving a specific task. One other aspect we are working on is helping our researchers with computer vision for solving some imaging task, this one is very interesting in microscopy, where we deploy the machine learning model for solving this imaging problem. So a microscope is normally a very well calibrated system for obtaining a very accurate view of samples, but there's still some aberrations that are not possible to model from the device. For instance, some samples are in general in a solution, and so active light that goes through the samples is being scattered by the composition of the sample itself and by the medium the light goes through. This creates a lot of aberrations in the sample, and the result is an aberrated image. So the idea is to obtain in real time to deploy a model that can resolve for these aberrations, since this is a physical since we don't know the exact sample we are gonna have to inspect, this can be solved in a data-driven manner. So to learn some coefficients about the distortion that can be then implemented by and distorting the image by piloting a deformable mirror that can obtain in very quick time, almost real time, an image that is corrected given the aberration that has been estimated by the network itself. Another aspect that I was mentioning before, and is very strategic to deploy any AI methods and that we are trying to support with our colleagues that even in robotics that are deploying systems that have cameras, is to obtain privacy preserving computer vision. So trying to let's say demask the images in order not to recover back identity of people. So this can be done, for instance, by scrambling the image source, like an RGB image, in order to provide information that can help you to solve the task, like a visual representation, that can be achieved both by software, by using even camera, by obtaining maybe even stream. But actually, what was thought to be a representation that is that makes impossible almost to recover the identity is not really it is possible actually with the network to do this event to image reconstruction and recover from the let's say this signal, the real signal, recover back the identity of people. So ideally the idea is to find models that can further entangle the information in order not to recover the identity, also against the inversion attacks. So a malicious person that try to train another model that is able try to attempt to recover the details of the person. So the idea is to create this event anonymization network in order to completely unscramble the identity information, while, for instance, allowing still the solution of some task. Otherwise, if the signal is meaningless, that will be meaningless for any task we have. So we have two competing networks, one for anonymization and one for task solving that have to be trained together in order to scramble the signal, avoid an inversion attack, but still solve a task like identification or where a person has been in different location of an area. And actually, this is all computational. What we are trying to do in collaboration with our colleagues at IIT that work on meta surfaces is to create a lens that embed this scrambling effect already on the physical layer. So this has to be done in a particular way where we deploy a network that has a first set of layers that are physics informed. It means that we estimate coefficients of the lens to be implemented physically on the device that do the scrambling at a low level, and while another part of the network that is able to achieve a task, for instance, pose estimation. So try to eliminate the details of the face of the person that could identify them, but still do pose estimation. So here we already fabricated a set of lenses, but soon we are trying to experiment on a real physical device. So we are going to have now a camera that is privacy by design, but in the physical sense as well, not only on the computational sense. So in the last part, I would like to talk about with other aspect of teaching science to computers, which is very interesting, at least for me in this part of activity and life, is to create models that are making our robotic platform autonomous. And our platform that we're working at the moment is called an ErgoCab, that was invested of INAIL, which is a center for that deals with the insurance of worker. So, and in practice, it works a lot with the disease that are work-related, the musculoskeletal disease I was mentioning before. So one idea is to create a robot that starts from our previous and famous version iCab that can interact with the human and support the human during work activities. So this is the robot. This is a sequence. You see, the robot is 1.50 meters of height and 60 kilos of weight. And at the moment, the robot you see here is teleoperated. So there is a person with a physical device, I will show you later, that is moving, and the robot is mimicking the movement of the person. So here you see that the robot can carry up to 8 kilos weight. It can operate a machine through teleoperation, and also is able to open doors and to manipulate small objects. So the thing we are using to teleport the robot is this device that is both given some manipulators and headset, and the robot we are able to mimic to transfer the motion of the person into the robot itself with a quite strong accuracy. Of course, the person is able as well to work. In that, we need some intelligence for the robot not falling down, because equilibrium is very difficult to transfer from a person to the robotic platform. Here you see an example where we were in London, in Accra, where the robot was teleoperated from Genova. So we can teleoperate as well at distance and not being on the premise. One of the the product we derive from the teleoperation, since we need to teleoperate, we need also the body joint posture of the person. We developed this technology, it's called iFeel, that is able somehow to model the pose, also the stress, the physical stress of the person, because we have also sensorized a set of shoes that are, so we are able to estimate the strain, the fatigue as well on the person when carrying weights or doing some manual operation. So, so here we are able to, by teleoperation, this is very interesting for us, and this was an enable aspect of what we are going to do. The robot motion, vision, and all the sensor when doing the task. So this it starts to put a circle where we do task, we generate data, and then we can build models that mimic through imitation learning this operation. So we can provide autonomy to the robot itself. And this was one paper we did last year, was one of the first research model for autonomy on the humanoid platform. Here you see the video on the left. The robot is not teleoperated, it's already moving autonomously, given some visual feedback, he do some operations that has been instructed to. So it's not generalizing at the moment to, at the moment of this video, it's not generalizing to different operation, but the idea is to find models that better mimic the teleoperated data that we have. And at the moment, we also integrating not only the visual and depth and other sensor from the robot, but also language and text. And the nice thing is that these models can also generalize to different environment. This is in a stage of an event where the teleoperated person remove all his equipment and the robot starts to move autonomously. This is one of our staff, do some gesture, he reacts to some behaviors that he's seeing from the person, but not in the lab. So still outside the lab. And he can also, let's say this is Daniele Pucci, one of our PIs. He can also be inactivated from suggestion and start to work and follow you on the stage, hold hands and other actions. I said that we are doing also you integrating language, speech. I'm not sure if you can hear the video, but I don't know. Now. Sorry, this is not turning out well with the audio, but in practice, what happens now, we are looped two robots that are talking each other. So one of them is talking about his function and the other one agrees because it's the same copy. But yeah, this is a pretty interesting behavior we have at the moment. So this is to be clear that the language, the images and the sensors like the motor currents are all input to the same model. So they're conditioning signals for the robot. They are not pre-script. Okay, so we actually don't know how the robot is going to reply or say, because indeed this is is not prescripted at all. At the moment, we are, and this is my concluding part, we are trying to perform more complex skill, okay, saying hello and holding hands and other things. They don't require too much precision. So at the moment, we are going into, let's say, a factory-like automation aspects where the robot has to hold objects, leave them, pick and place in order to incrementally learn this scale with all the possible complexity that you have, because the objects are general purpose. They arrive from different location, they have different weights and size, and also the teleoperation is not so trivial to do in such aspect, as you can see while leaving the objects into the box. Okay, but in order to do this task, you need a very good modeling of the surrounding environment. So it's very key to have a very precise information of the 3D structure of the space, how objects are arranged and where they are, and which is the pose. So to effectively grasp them, manipulate, or anyway activate them in the surrounding environment. So for this reason, we invested a lot of work in developing what's called a spatial AI. So in the past, it's called 3D vision, but because we don't only want to digitize and model the 3D environment, but we also want to have a semantic representation of their environment as well, and also to interpret and understanding it at the moment. So how to do that? Our objective are three at the moment. One is to do a modeling, a visualization of the environment as much as realistic as possible. Probably, I'm not sure if you've seen the last NVIDIA GTC. There are new tools that are able to simulate the robot in different environments. In the simulation, if they are realistic as much as possible, they can provide you a lot of training data to generalize the robot functioning. Also, other autonomous device in logistics and other environment. And also, we need as well to put the recording I showed you before in context. So all the information we extract, if they are aligned in the 3D world, we can know where the robot is performing task at which position. And the other objective is to enable spatial reasoning. So by using 3D semantic map, we can deploy or learn new tasks for exploration and planning inside any type of environment, if the simulation, of course, is good enough to perform it. So how we do it? We use an overview synthesis models that are able not only to reconstruct the 3D of the scene from a set of input images. This was a video that one of my students took while at the restaurant with his mobile phone, but they can also render novel views in a very accurate way. So we can model, for instance, a camera moving around the scene, but also a robot moving around the scene. And you see that the modeling is pretty much accurate of the generated scenes we see here. And so what we do, we start from a set of images. I show you here. Normally we start from an intermediate 3D representation, classical, like 3D points, very sparse in the scene. And then you use this other representation using 3D Gaussian that not only encode the 3D information, but also color information that can be projected, or now call it like splatted into the image in order to render the novel view. But what we are working a lot at the moment is not only to reconstruct the 3D scene, but also its semantic. So from the input images, we don't only want to reconstruct the 3D scene, but find where each object is, or each element of the scene is there. So we would like not only have a 3D representation, but a 3D scene segmentation and understanding where everything is to render novel view, select objects, and do multi-view segmentation. So I'll go quick here. So starting from visual representation, we can encode feature field at each one of 3D element, and this 3D representation is consistent, and we can actually click over some objects and see the scene in different viewpoint, and also remove this type of objects or the other objects, so I have a total complete control of the digital scene we have in the moment. And at the moment, we are progressing further in this topic because we also want to connect to the 3D representation also language models, so we can by speaking select some objects. And this is useful also from robotics because we can instruct by words the robot to go and pick an object, and the robot know exactly in 3D where this object is represented. And we would like to do this in fine-grained way. I would like to complete with this very Japanese example. We we reconstructed this restaurant scene again with a 3D GS model, and the idea is to decompose in fine grain all the different elements of this scene, so to create a three-language field that can be used to have a hierarchical semantic, for instance, for this bowl of ramen, to divide all the different elements, not only the object per se, but to divide all the elements in 3D and also in 2D in a fine-grained way. And this is just an example where in the scene, this is rendering as well the scene, and this is the 3D model underlying it. We can very well cement the chopstick given a text input, the kamaboko, I hope my spelling is correct, and as well a glass of water. And this is a pretty amazing and interesting because you can get a very well fine-grained cementation and control of the scene at a very tiny 3D elements of it. And these are other qualitative results about localization, where we are able to, compared to previous approaches, to obtain compared to the ground truth for this sake cup in the environment, quite accurate localization, also in other scenes, but very tiny elements as these cookies, which are 3 here, are very well estimated and cemented, which is not really a trivial task given this type of elements. So I conclude here my talk. I hope it was very interesting. I leave you ground for questions. I cover really a lot of topic with this presentation, but feel free to try to ask, and I will try to respond. Thank you very much.
Thank you, Alessio, for the great presentation. We have questions from the audience. So, Meg.
Thank you for the great talk. That's very nice overview of the activities in IIT. So I'm working on rote learning. I'm curious about the automation of humanoid robots in your lab.
Wow.
So recently many researchers are working on large-scale models. So now people are trying to develop generalist models such that the model can be used for various tasks. And then, are you going for such a direction, or do you focus on a model that works on a specific tasks? Because the recent generalist model does not work well sometimes. The success rate is not so high, like 80% or something at most. So do you go for such direction, or do you go for a model for specific tasks in the real world?
This is a great question, and something that I didn't focus too much. Our target has been always to deploy the models on platform and not to have this on cloud. So what the autonomy we achieved was running directly on the robot. And large-scale models at the moment, the tiniest we have is around 2 billion parameters, which are a bit complex to put into the computation hardware of the robot, but in general it's like a Jetson type of GPU. So indeed, there is a complexity in making run these models directly on the robot. So you have to use cloud services, and so you increase the latency and the cost. Something that for application is very tough to use. And besides, is correct. We have the success rate for some set of actions are not sufficient to deploy them in a realistic environment. So my point of view is the following: is if everyone will ever buy a robot for doing some task, their environment is going to be quite restricted. Okay, especially in industrial domain. In household domain, we can discuss about it, but in the industrial domain, I would say that the robot is gonna do 10 tasks or 20. So it's very important to have general purpose models to give a generalization given the different aspects of what's happening, but we need very specific models that can solve with accuracy the task. And it doesn't mean that this has to be all true end-to-end. Some of the last steps of the task where you need very good accuracy, even millimeters, maybe an end-to-end model is an overshoot for that, or is not capable to do it. So I would say the desiderata is not to have a very large model because it has to work on the robot, and also the task has to be smaller because anyway we will not have too many of them. In household, it's a bit different because a household robot has to solve several tasks, so it's not very clear the solution if everything could be embedded into the robot itself, because you need also some communication skills that are quite large in respect to a small language model you could impose into it. So, I mean, many issues are still open. I hope I did some directions over it.
Thank you very much.
So, Mike, please.
No, I have several questions, but maybe the main one will be about the aging. So in your kind of like approach to support aging societies, would you like to kind of replace the function of elderly people, like, help them, I don't know, make cleaning, cooking, and so on? Or would it be more important to stimulate people to keep them like, in the loop? So basically like, maybe helping with some daily jobs, but maybe mostly like stimulating cognitive function.
Yeah.
So which of the approaches would be?
Yeah, I show you a lot of monitoring, but and that's passive mainly, or you can, but the idea is the monitoring should be the basis for understanding which stimuli to provide to people, and I believe I believe with you that the person has to be stimulated to be active, to just create spaces where the person is protected, but is just going worst in his condition day by day. This is not the aim, and I agree that the stimulation and find the way to a better stimuli for the person to be more active, and if we cannot stop the disease, of course, to reduce its impact of his life is important. And I know that you are working on this, and of course we can target some specific application on that, or further collaboration in this point.
If I could get one more question, because you mentioned you run this kind of machine learning models in the robot. So basically, each robot must be highly personalized. Basically, your robot would be different than my robot. So how do you what is your strategy to update the models? Do you have like some kind of federated learning, or kind of preserve privacy and security, but also to keep the model as updated as possible inside the robot?
Yeah, that's a very good question as well. And model update is a major issue because you don't want to retrain from scratch, and this is an issue. So we are actually some people in IIT are working on incremental learning or lifelong learning. So to have models that given continues or spot new data can quickly improve without forgetting the previous skill. This is, of course, a known topic in machine learning. At the moment, the simplest thing is to add in a flexible way new skills using a new set of parameters that helps not forgetting the other one, because we increase the skill by increasing the complexity of the model. Of course, you know, this lead you to another problem, because we cannot increase dramatically through time. Otherwise, we increase too much the memory size and the model complexity. So this is an open question as well, how to do it, especially if you want to deploy for real personalized robotics, because this has to be stable and a guarantee that the model is working. And of course, other problem is not going against some guardrails you imposed in the model, especially when you have to apply in a realistic scenario.
We have a lot of participants online, actually, nobody's asking questions. So you have this like a brain and machines, and then later on you have this robotics. Are they connected? Like, you know, you have the two robots talking to each other, and first you have the brain and machines. Are they connected?
Yeah, they are connected, and of course, given the complexity of the topic, some overlap is also necessary between the two. The approach are different somehow. On some aspects, we rely a lot on computation, on machine learning models. On the other side, there is more research on the cognitive process that underlines that intelligent is the basis. So the approaches are different. I don't say they are completely separated from that, because there are a lot of interconnections. But this is the thing that is stimulating in these flagship problems, because there will be different conclusion, and this is I don't say that the solution is only one, especially in a problem which is so loosely let's say defined as intelligence.
Okay, thank you very much.
So currently I'm working on reinforcement learning, and then in your future topic, you also included reinforcement learning. So are you going to learn some kind of superhuman performance using the reinforcement learning on your humanoid or something? Or could you tell me some plans for your work on reinforcement learning?
Okay. It's good that you work on reinforcement learning, because we need such expertise. We have some people working on reinforcement learning, and we actually work with them. And it mainly is dedicated on the online update of models. We have a very big problems in robotics, that we take some models that have been trained with the data that mainly comes from the internet or from a database, and then we deploy the robot in a scenario which is very specific, and we see a decrease of the performance in object detection and other visual tasks that are really important for the robot itself. So the idea is when these cases happens is to deploy strategies for self-learning. So the robot, by navigating the environment, should improve their capabilities by understanding that is making mistakes. This is really one perfect application for reinforcement learning. So we can create a reward for the robot to explore the environment in a way that is failing the maximum as possible. So it can learn creating pseudo labels about the mistakes he did. We can go in more details about this work, but indeed this is one of the application. The other one, you say, for this superhuman skills is correct, because imitation learning is based on the data we collect from a human operator that has to operate a robot. So is everything based on the skill of the operator, and also on the difficulties on the fact that he's trying to embody a body which is not his. So the efficiency is not as the maximum as it should be, because there is this barrier. So indeed, the simulation, the realistic simulation we are trying to achieve with an overview synthesis and other 3D vision approach will be useful to simulate in an environment as much as realistic as possible the operation. This is a field for which we need reinforcement learning a lot.
Thank you very much. Because so here we do not have real robots, but we are working on algorithms, and it would be great if we could have some collaboration between us.
Yes.
And then,
This is the reason I'm here.
yeah, let's talk about this later.
Of course.
Okay, there are no further questions, and let's thank Alessio again for the great presentation.
Thank
you very
you.
much.
Thank you all. Thank you all the people online.